Einstein's theory of special relativity is perhaps the most famous theory in all of physics. It gives rise to the infamous formula, E equals mc squared, which was used in the production of the atom bomb. But what does that formula actually mean? What is special relativity all about? What is the relationship between space and time? This short video will try to give you some idea about the answers to these questions. I do not know if I explained it very well, and this may seem very confusing and hard to understand, so I apologize in advance if that is the case. I am by no means an expert, and am still a student myself, never having studied relativity formally, but when learning about special relativity I found free online resources very useful, and have decided to produce the video that I believe I myself would have found most useful when reading about relativity for the first time. To understand relativity, we must begin with Galileo, the founder of modern science. Before Galileo, it was believed that any moving object would gradually come to a stop. This idea was based on the observations of motion on Earth, and although a naive belief, it is certainly an understandable one. What Galileo realized was that any moving object would continue to move at a constant velocity unless an external impulse of some kind was applied to it. The reason we never see this happening on Earth is because air resistance and friction provide a consistent force against motion which brings any moving object over time to a state where it is stationary with respect to the Earth. In an ideal world without air resistance and friction, moving objects will continue moving forever. Despite the fact that we do not live in an ideal world, it is still possible to see examples of why Galileo's ideas must be true. Imagine you are in a train traveling at 100 miles per hour, and you jump up in the air so that you are not in contact with the train. The train is moving at 100 miles per hour. So why do you not fly backwards? Why does the back of the train not hurtle towards you? The answer is that while you are in the train, you will continue to move at 100 miles per hour until an external force is applied. You only feel pushed back in your seat when the train is accelerating. Once it has a uniform speed, then you can move around in the train just as you could on the ground. There are no strange forces pushing you backwards. A fly is able to fly from the back of the train to the front of the train perfectly happily, even though to an outside observer the fly appears to be traveling at hundreds of miles per hour. Because once the fly has a certain velocity it will retain it unless external forces are applied. In this example lies a fundamental principle of physics, called the principle of relativity. If you are in what is called a frame of reference traveling at uniform velocity, like a high-speed train, the laws of physics are exactly the same inside the train. That is another way of saying that there are no spooky forces pushing you back in your seat. Everything in the train behaves exactly as it would if it were on the ground. Any machine which operates well on the ground will operate equally well in a train moving at uniform velocity. This is because all objects in the train will keep their velocity unless a force is applied, just as all objects on the ground will remain stationary unless a force is applied. We can extend this principle and say that it is impossible to say that the train is moving, because everything in the train behaves in the same way as everything on the ground. Who are we to say that the train is moving and the ground is stationary, and not the other way around? The principle of relativity says that it is impossible to say that one person is moving and the other is stationary. We can only talk about motion relative to something else. We can say things are moving relative to the Earth, or that the Earth is moving relative to the Sun. This principle is a rather beautiful idea, and it was believed to be correct right up until the 19th century, when scientists began investigating the nature of electromagnetism. The problem came when the physicist James Clerk Maxwell unified the laws of electricity and magnetism into a single set of equations known as the Maxwell equations. The problem was with one of the constants in the equations, which we give the name c. Maxwell calculated in his equations that it was possible for waves to propagate through an electromagnetic field, and that their speed would be given by c. When he worked out what c should be, he found it matched almost exactly the experimentally observed value of the speed of light. Maxwell had made an amazing discovery. Light was an electromagnetic wave. The problem with this discovery and the principle of relativity is this: if the principle of relativity is correct, the laws of physics cannot make reference to a speed, as the Maxwell equations do. To see why, ask yourself which frame of reference the Maxwell equations apply to. The Maxwell equations predict a speed for light, but the speed of light will be different depending on how fast you are moving. An observer in a train traveling in the direction of a light beam would see it move more slowly than someone on the ground, because they would be traveling along with it. The Maxwell equations must be different to people moving at different velocities, so the laws of physics are different when you move at different velocities. So a machine which works on the ground may not work in a train if it relies on the speed of light in some way, because the speed of light would appear different. It is possible to say that someone is moving and someone is still, by defining the stationary reference frame to be the frame in which light travels at speed c. The scientists called this stationary reference frame the ether, and they believed that light traveled through this ether. It was always possible to tell how fast you were moving with respect to the ether by measuring the speed of light. This was mildly annoying, but not catastrophic. Yet another principle of science had to be abandoned because it disagreed with experiment. But that is what scientific progress is all about. In 1887, two scientists Michelson and Morley decided to measure the absolute speed of the Earth through space. That is with respect to the ether, as we said should be possible above. They did this by measuring the speed of light in different directions, assuming it would appear slower in the direction we were traveling towards and faster in the direction we were traveling away from. What they found was remarkable. Whichever direction they measured in, the speed of light was the same. They had discovered that the Earth was stationary. This cannot be correct because we know the Earth is rotating around the Sun. Its velocity is changing, so it cannot always be stationary. This left a mess, because it seemed that when it came to Maxwell's equations, the principle of relativity still appeared to apply. However fast you were traveling, light always appears to travel at the same speed relative to you. If you are in a train and you flick the front lights on, you will see the light heading away from the train at speed c, and someone on the ground would see the light heading away from them at speed c too, even though they and the train were traveling at different speeds. This seems paradoxical, impossible even, but it is an experimental fact, so physicists had to live with it. It was clear that the central problem lied in the equations for working out how fast things should appear to be traveling at different speeds. It had seemed intuitively obvious to all previous physicists, including Galileo, that velocity transformations should be simple addition rules. If a man on a train moving at 100 miles per hour is running at 3 miles per hour with respect to people on the train, then to someone on the ground he appears to be moving at 103 miles per hour. If we are to accept that the speed of light is constant in all reference frames, we must reject this rule and come up with a new one. But which rule should we pick? The problem was solved by Lorentz, who came up with a set of equations, the Lorentz transformations, which described how things should change when you look at them at a different speed, in order that the speed of light appears the same and the Maxwell equations don't change. These equations required a range of weird phenomena to occur, such as time dilation, which said time should move more slowly for things with a high speed, and length contraction, which said that things moving at a high speed should get shorter. But he had arrived at a mathematical model of the universe which could explain the experimental observations, even if it appeared rather arbitrary and counterintuitive. Although Lorentz had come up with these transformations, he still believed that the ether was necessary, and that the principle of relativity was invalid. This was because, although the laws of electromagnetism were now the same whatever your velocity, the laws of mechanics which were described by Newton could not be made consistent with the Lorentz transformations, and so they could only apply if you were stationary with respect to the ether. Basic rules like conservation of momentum are now only correct in one reference frame. Lorentz had left physics in a mess.